explain what is meant by the capacitance of a capacitor, and again I'm not going to explain that again. And then the next experiment's about the reed switch, which again you don't need to know anymore. So we'll just go on to part C there. A capacitor of capacitance 2 microfarad is charged by connecting it to a battery of EMF 9 volts. Calculate the electrical energy stored in the capacitor. And so I'll just write this on top here. So you've got a capacitance, this is 8C. You've got a capacitance of 2 microfarads. And you've got a voltage of 9 volts. And it asks you to calculate the electrical energy. So just using those values, E is equal to half CV squared, which is a half times 2 microfarads by 9 squared. And that gives you an answer of 81 microjoules. The next part of the question, here comes this kind of question again. The charged capacitor is disconnected from the battery and is immediately connected across an uncharged capacitor of capacitance 6 microfarads. Now, immediately you know that whatever charge was here beforehand, it's now been shared with the 6 microfarad. The voltage is going to drop. The voltage across both of them is going to be exactly the same, and I'm just going to draw that in and call it V. So it says calculate the electrical energy now stored in each capacitor. So what you need to know there is either a charge for each capacitor or the voltage for each capacitor before you can actually go and do your energy sum. So we'll find the voltage for each capacitor, voltage across each capacitor. So I'm just going to redraw this again. You've got 2 microfarads and 6 microfarads. This is part 2. That was 1. And this one is now part 2. Straighten that up a wee bit for you. And we're trying to find our voltage here, V. So we can find out the initial charge Q. Up here in this question, you know that Q is equal to CV. And you had 2 microfarads and you had 9 volts. So that's a total charge of 18 microcoulombs. Microcoulombs. Microjoules even. No, microcoulombs. I'll just keep going. You don't mind me making a mistake, I'm sure. So QT is equal to 18 microcoulombs. The total voltage then is equal to your total voltage then is Q over C. And so Q is 18. This is in parallel. So adding the capacitors in parallel, you just add them, you get 8 in the bottom, 8 microfarads. And that gives you an answer 2.25 volts. So now you're ready to do your calculations. You know the capacitor across each capacitance of each capacitor, and you know that each one has a voltage of 2.25 volts. So for the 2 microfarad capacitor, the energy is equal to half CV squared, which is equal to a half multiplied by 2 microfarads by 2.25. And so the energy comes out there to be 5.06 volts. And then the second one, the 6 microfarad, E is equal to a half CV squared, and that's equal to half by 6 microfarads. I didn't square that over here, but I did in the answer actually, by 2.25, and that's equal to 15.19 or 15.2 microjoules. And this is also microjoules. But I knew you knew that anyway. Okay. There's the answer to the two answers. 5.06 microjoules and 15.19 microjoules. Okay, it says account qualitatively for any difference between the total electrical energy stored across the combination of capacitors in part 2, which is this part here, up here, and the energy initially stored in the 2 microfarad capacitor. Well, there's much less energy in total now. You've got 5.06 plus 15.19, which gives you 5.06 gives you 20. Now you have got 20.25 microjoules, whereas before you had 81 microjoules. Now, what you have is the same charge available to the two capacitors now. You now have the same charge available as you had here. You've still only got, did we do a calculation? We did. We had 18 microcoulombs in total. So in both cases you still have the same charge, but now you have got a much larger capacitance. And you know the equation, E is equal to a half CV squared, or a half Q squared over C. We derived that in one of the other questions there. So E is equal to half Q squared over C. And if you have the same charge, but you have different capacitances, or a different amount of capacitance here, you're going to have less energy. So we've got more capacitance now in our new circuit, the same amount of charge, and therefore less energy stored. Okay, the last page then.